Okay, so in this tutorial, what we're going to look at is dependent events. So probabilities when events are dependent on one another. So how can this be done? Well, the basically what we're going to be looking at is you calculate the probability of two dependent events. So let's say A and B. And how you can do that is simply by multiplying the probability that A occurs by the conditional probability that B occurs given that A occurs. Now, that's a lot of words there to think about, but really what it's saying is this, and the notation is such that when we look at it, we say that this little intersection here, so this is as where the event A intersects with B. So another way of reading this is the probability of A then B. Okay, so that's a way of thinking about it. Another way of thinking about it is A and B. Okay, so if you read it as what is the probability that A then B happens? And I'm going to explain how we get to this equation here shortly. So how you can find it is just simply the probability that A happens and the probability that B happens given that A occurred. So if you want to find out the probability that A happened then B happened, you take the probability that A happened and multiply it by the probability of B given that A happened. So let's take a look at some examples, and that will really help you understand sort of what's happening in this situation. So basically, the probability of a second event occurring, given that the first occurred, is really important because the sample space for the second event is reduced from the first event. So if there were 10 objects, after you've taken an object out, there's only 9 objects during the second selection. So because of that, they're dependent on one another. And so, we're not replacing the items back, we're taking them out and removing them. So here's some important points to make between independent and dependent. So whenever there's replacement, the events are considered to be independent. So the chances don't change in each of the subsequent events. So we've done lots of examples like that. Without replacement, that's when you take an object out perhaps, and now there's less objects in there in the sample space, and so therefore the chances or the probabilities change. Okay, so let's take a look at an example and kind of work through an example and see how this works. I've got a little diagram of a situation where there's a bag that contains 5 marbles. There's 2 that are blue and 3 that are red. So there's 5 total marbles. That's represented here in this tree diagram. You can't tell, but in this bag here, there are 2 blue and 3 red. Now you can tell some information just by the probabilities as they work through here as to which color is which, even though you can't see them on here. So let's say that we were asked to calculate the probability of drawing 2 blue marbles. Okay, so we want to draw 2 blue marbles and find out what the probability is. Well, you can look at this from our tree diagram. Now, there were 2 marbles that were blue and 3 that were red, so here's 2 over 5. So that clearly represents drawing a blue marble. The probability of getting a blue marble is simply 2 over 5 because there's 2 blue out of 5. The probability of getting a red marble is clearly 3 out of 5, so this represents drawing a red marble. Now up here, if we've already taken a blue marble out, there's only 1 marble left. There's only 1 blue left, and there's 4 total. So if there's 1 marble out of 4 total, we know that this is drawing another blue marble. And the case below, that's a red marble. So in here, we are left with 1 blue and 3 red. And here, if we've taken a blue out, we're left with simply 3 red. So even though you can't tell the colors, you can tell from the probabilities what's happening. And subsequently down here, this is actually harder to see because the probabilities are the same, but since we've taken a red out, this could represent a blue and a red, and in which case you would have all blue or a mixture of the two. So it says, what are the chances of drawing 2 blue marbles? Well, if we started out here, we select a blue marble, select a blue marble. That's the only pathway in which two blue marbles are drawn. There's no other way that you can go, this is blue, red, red, blue, red, red. So it doesn't work. So that's the only way to get the two blue. Well, that's a 2/5 multiplied by a 1/4 is a 2/20. Now 2/20 reduces to 1/10. So there's a 1/10 probability of getting two blue marbles. Dependency, because I'm taking the objects out. So let's take a look. Using our formulation up the top, I'll move it up a little bit here so you can see. There we go. So here's our formulation. What is the probability of drawing a blue marble, then another blue marble? See how I said that as I wrote it? That's the key. Well, it's the calculation, it's the probability of drawing a blue marble multiplied by drawing a blue marble given that I've already drawn a blue marble. Again, see how I just used the words to explain it. The probability of drawing a blue marble from the beginning is clearly 2/5. There were 2 out of the 5 was there, and that's this situation here. Now there's only 4 objects left. Notice how this dropped by 1. The sample space dropped by 1. It reduced from the first event in this case. Now, if I want another blue marble, it's there's only 1 blue marble left out of 3 red, so there's a total of 4, and there's only 1 left. So that's 2/20. It matches the tree diagram perfectly, as it should. And this clearly reduces down to 1/10. Okay, let's give this a shot for the next one. Calculate the chances of drawing a blue marble, then selecting a red marble. So notice it's saying then, there's order involved. It's saying blue, then red. So it's the probability of drawing a blue marble followed by a red marble. Well, it says conditional probabilities or the dependent events say that in this conditional probability, we're going to say what's the probability of drawing a blue marble, and then the probability of selecting a red marble, given that a blue marble was already selected. See how you can just read it right through. So the probability of drawing a blue marble initially is 2/5, following this path, and now we've taken out a blue marble, so there's 3 red and 1 blue left. So what's the probability of drawing a red now? Well, the probability of drawing a red marble now is 3/4, like so, and that's 6/20, which reduces to 3/10. Okay, so this path, this gave us 1/10. This gave us, in this case, it was 6/20 or 3/10. You'll notice that if I follow this along, if I did this probability here, it's 3 times, that's 6/20. And then we've got also 6/20. 6/20 plus 6/20 plus 6/20 plus 2/20 is 20/20, which equals 1. So the probability is always equal to 1. That's so important to recognize, that it always equals unity, or 1. Okay, let's try another one. Calculate the chances of at least 1 blue marble. Now I'm going to show this in 2 ways. You're going to need a little bit of space for this, because there's 2 different ways of doing this. One is called the indirect method, and the other one is going to be the direct method. The indirect is faster, I think, for the most part, and the indirect is going to take, the direct method will take a little bit more time. So how do we write this? And again, I said you're going to need some room for this for sure. So the probability of at least 1 blue equals, well, here's the thing. If we look up here at our tree diagram, here's 2 blues, 1 blue, 1 blue, and yeah, this is blue, this is red, like that. And so that's, now we can see that that was a blue and that was red. It doesn't matter which one's which, but so in this case here, you've got that that has at least, so these two paths have at least one blue. This one has at least one blue. There's only one path right here that does not have a blue marble that was selected. One path. Well, what path was that? That path was 2 red. So watch what you can do. You can say, if I want to know when there's at least one blue, well, just get rid of the case when there is no blue marbles. Probability of at least one blue marble is just say take 1, which is the total probability of unity of 1, and subtract when there's no blue marbles. Because if I take the situation where there's no blue marbles, then I'm left with all the cases when there's at least 1. Well, how do we do that? Well, that's obviously the case when you get red and red. That's the only way that is. Well, what are the probability of getting red and red is the probability of getting red times the probability of red given that you already got red. The notation is a little crazy here, but 1 subtract. Now the probability of getting red in the first one is 3/5. The probability of getting red knowing that you already got red is now 2/4. And you're like, how did you get that? Well, there was originally 3 red out of 5. Then I took 1 red out, so there's only 2 reds left, and there's only 4 marbles in total. So this equals 1 minus 6 over 20, which is 14 over 20. We have a high probability of selecting at least one blue marble. Okay. Does that make sense? Absolutely. Think about it. If this whole thing is unity up here, and we had 2/20, 6/20, this could reduce to 7/10. You could actually put it down to 7 over 10, like that. But up here, you see if it's 2/20, 6/20, 6/20, 6/20, there's clearly 6, 6, and 2 is 14. Those 14/20ths where there's at least one blue. And in fact, that's the direct method. The direct method says simply look at the probability of at least one blue is the probability that you select a blue, then a blue, plus the probability you select a blue, then a red, plus the probability that you select a red, then a blue. This path, and that path. So there are 3 paths where that happens. Now, notice I had distinguished between drawing a blue, then a red, and a red, then a blue. That's important, right? Because the order in which you're selecting them does matter. The probability of getting a blue and a blue we already calculated was 2 over 20. The probability of blue then red was 6 over 20. Turns out that if you did the probability of red then blue, it's the exact same, except it would be 3 over 5 times 2 over 4, which is actually still 6 over 20. So I saved some work there just by thinking through it, and you get 14 over 20, which is 7 over 10. The exact same answer using the direct method. And again, I said the key point here is realizing that you've got the probability of the blue then red and red then blue. This indirect and direct method is going to come into play in this course for the probabilities section very often. So get used to this idea and try them both ways while doing this. And the tree diagrams are really helpful for understanding those situations as well. All right, let's take a look at another example here. Okay, so what we're going to look at here is just 2 other quick examples. A purse contains 4 $5 bills, 5 $10 bills, and 3 $20 bills. 2 bills are selected without the first selection being replaced. Fine. Find the probability of pulling out a 5, then a 5 again. So we know that's just what's the probability of selecting a 5, and what's the probability of selecting a 5 given that a 5 has already been selected. And by the notation, that should be the line. That was my mistake. 5 given that 5 was already selected. Well, there are 4 5s out of a total of 9, 10, 11, 12. And then now there's only 3 5s left out of a total of 11. And so you can quickly do the math here, and you get 12 over 132, which reduces to 1 over 11 probability. Okay. This next one is tricky to think about. And people often get stuck on this type of problem because it seems at first not to make sense. And it seems unintuitive as to what's happening. So it's known that 70% of your friends like chocolate, ice cream, and 35% of your friends like chocolate and strawberry. Calculate the percentage of your friends that like chocolate also like strawberry. So the percentage of friends that like chocolate and they also like strawberry. So let's write out what we're given, and then we're going to talk through this. The probability that they like chocolate is 70%. So, I can write it as a percentage. I can write it as a decimal. Doesn't matter. So I'm going to write it as a decimal, 0.7, since I'm talking about probabilities. And then it says that the probability that they like chocolate and strawberry, notice how I use the word and, a little bit obnoxiously, chocolate and strawberry, or chocolate then strawberry, is 0.35. What is the probability that they like chocolate given that they also liked strawberry? Reading it with that language is really, really important to understanding how to do this. So we read it out. The probability that they like chocolate and strawberry is equal to the probability that they like chocolate times the probability that they like chocolate given that they also like strawberry. This number was 0.35 and this number was 0.7, and we're trying to find out this information. Some simple rearranging. Is this, and so the probability that they like chocolate given that they also like strawberry is, so that's half of that, so it's 0.5, so it's 50%. So 50% of your friends who like chocolate also like strawberry. And you're like, it just seems so odd because you're like 70% of them like chocolate, 35% of them like chocolate and strawberry, but 50% of them will like chocolate, who like chocolate will also like strawberry. So 50% of the number. So basically it's all of these people like chocolate and strawberry. 70% of your friends like chocolate alone, so therefore that's 50%. So 50% of them like chocolate, or who like chocolate also like strawberry. So again, you got to wrap your brain around that. Another way of thinking about it is with a little Venn diagram. And we're going to learn more about Venn diagrams later because they're very, very handy. Let's imagine that we have all your friends here, and we have another set of your friends here. Now let's just pretend for the sake of argument you have 100 friends. That's chocolate, and there's strawberry. The intersection tells us people that like chocolate and strawberry. Well, we know that's 35 of your friends. So if you have 100 friends, and you ask them, and 35 of them said, I like chocolate and strawberry. Well, you know that 70% of your friends, or 70 of your friends, like chocolate, right? Well, if they like chocolate, there's only 35 people left. 35 and 35 is 70. So 70 of your friends like chocolate. 35 of which just happen to also, they like chocolate and strawberry. And then it says that there are, that's 70 of your friends, so there's only 30 left that like strawberry. So that 70 plus 30 is your 100 friends, to get that percentages of 70% and so on and so forth. So 35% of 100 is who likes chocolate and strawberry. 30% of your friends like just strawberry. 35% of your friends like just chocolate. So what's the probability, or what percentage of your friends who like chocolate also like strawberry? Well, That's easy. It's 35 of your friends who like chocolate and strawberry, and there's a total of 70 friends that like chocolate. And that's 0.5 or 50%. So it matches again. Okay. So there you go. That's a visual way of explaining that type of problem. What you're going to do is work through the rest of these questions. You can go to this website, and when you're at this website, you can type in your answers as long as it's reduced fractions. So you got to leave everything in fractions, and they must be reduced to check your answers. And you're going to answer these questions and check it on the site. A hint for this one here, it says 1 red marble and 1 blue marble. It doesn't say 1 red then 1 blue. It says 1 red and 1 blue. So the hint here is that's the case I taught you about on the previous page, where it's the probability of red given blue plus the probability of blue given red. Or, sorry, the red then blue and then blue then red. So you need to look at both cases. They're often just the same number, but so you're basically just taking one of them and multiplying it by 2, but you can check that for yourself. All right, so try the rest of these questions and then check them with this answer sheet and see how you do.